Hello everyone, I am Junaid Rahman. I am a PhD student at Technical University of Lords. Today, my presentation topic is analysis of isolated branches of periodic orbits in 1 degree of freedom parametric oscillator. Here is the outline of my presentation, systems description, analytical solutions, and at the last, discussion of obtained results. Here, I have we have experimental stand of 1 degree of freedom parametric oscillator, which is present in our lab. And let me explain this experimental stand. This setup shows, this setup consists of two oscillators 7 and 10 connected by a rotating shaft 5 with a rectangular cross section. In both oscillators, it is possible to measure the displacement along the profile rails 9 and 12. And for the profile rail 12, the roller is marked with the symbol 13. Both cars 7 and 10 are equipped with a manual brake 6, which block their movement along the profile rail. Moreover, each card is permanently connected to a Hall sensor 8 and 11. In this presentation, in this work, we have analyzed this system 1 degree of freedom. So we have restrict the other, actually we have two trolleys. So we allowed to move one trolley, and we have restricted the other trolley, number 10. And here these two trolleys are connected with each other by a rectangular shaft. And here the shaft is supported in two bearing blocks 3 and 15, where the clamps 4 and 14. The bearing block 3 is placed on the movable cart 7 and together with the clamp 4. So the bearing block 15 is placed on the fixed cart 10 and together with the clamp 14. It restrains the shaft. Clamps 2 are used to mount neodymium magnets 1 that provide non-linear stiffness in the system. So in the next slide, we have a dimensional and non-dimensional equation of motion of this system. So by using the second law of equation of motion, and we get equation 1 represents the dimensional form of equation of motion of our system. And then we're going to convert the dimensional equation into the non-dimensional equation. So we have defined non-dimensional time variable tau, and where the omega n is a natural frequency, and we have defined the non-dimensional displacement y, and omega is equal to 5 prime is the non-dimensional angular velocity. So after these, substituting these non-dimensional variable into equation 1, we will get equation 2. So here we have introduced the following parameters and expanding the magnetic stiffness in equation 2 into Maclaurin series and limiting it to the fifth term, and we will get equation 3. So here, dry friction term, we have denoted F naught of y prime. So we have defined here in equation number 4, which a signum function, we have used here signum function as a dry friction. And here we have stiffness characteristic for full nonlinear model, and its approximation by third and fifth degree polynomial. So if we see here, the fifth degree polynomial shows the more accuracy as compared to third degree polynomial. So in here we have used method of multiple scale and harmonic balance method to analyze our non-dimensional our nonlinear model and the non-dimensional form, final form of equation 3. So we are going to use multiple scale method to analyze non-dimensional equation. So firstly, we have multiplied nonlinear terms with epsilon to balance the terms. And then we have defined here different time scales, T0, T1, T2, which represent the fast time, slow time, and even slower time. And so now we will convert our single valued function into multi-valued function. So that means we will find a solution of y in terms of variables in terms of t naught, t1, rather than finding a y in terms of tau. So when we will use multiple scale method, we convert our nonlinear ordinary differential equation into partial differential equation. And then, we have supposed the general solution of equation 5 in the form of equation 7. And then we have calculated derivatives in equation 8. And then we have substituted equation 8 and 7 in equation number 5. And comparing the like terms of powers of epsilon, we have equated the coefficients of epsilon power 0 and 1 equal to 0, and we got equation 9. And we can easily compute the solution of equation 9a in equation 10. And then equation 10, we have substituted in equation 9b. We'll get equation 11 here. CC denotes the complex conjugate terms. So if you would like to see over here in equation 11, we have secular terms. So we want to remove the secular terms, so we will use solubility conditions. The positive powers of exponential function, we will collect and equate it to equal to 0. And then we have defined a new polar form. A is equal to half of a e power iota beta, where capital A, small a, and beta is a function of d1. And then we have calculated d1a and substituted into 12, and we get equation 13. So after comparing the real and imaginary part, we will get equation 14. And the modulation equation become when the system is made autonomous, not any explicit in T1, by using psi is equal to zeta by 2, T1 minus beta. And then we'll get equation 15. So for the fixed point, we'll put the first derivative of amplitude and psi prime is equal to 0. We'll get equation 16. And then scaling and adding 16a and 16b, and we will get equation 17. After simplifying 17, we will get the 10th degree polynomial equation in terms of amplitude in equation 18. So in the next slide, we have employed harmonic balance method to analyze equation 3. So here we have utilizing a Fourier series formalism of angular displacement, considering only a single harmonic below equation 19, where A is amplitude and beta represented as phase. So the dry friction phase is extend as well, employing a single term Fourier series of the form equation 20, where Fc and Fs represent the coefficients of other coefficient of expansion, the derivative of the addition outlined in 21. Substituting equation 19, 20, 21 in equation 3. And after some calculation, we will get 22 equation. And then we have calculated Fc and Fs for the coefficients. So equation 2, dry friction term to find Fourier coefficients, use equation 4, which in equation 4, we have defined dry friction function. So then the coefficients read as in equation 23. So using equation 23 into 22, we get 24. For A is equal to 0 is a trivial case, and it is not a solution to the above system. So squaring and adding equation 24A and B to eliminate the 2 beta, which give us amplitude in the following form in 25. So again, we have 10th degree polynomial. And then we have calculated beta in equation 26. So now we will discuss our obtained results in the form of graphics. So here we have compared obtained results. HB3 shows the harmonic balance solution in third degree polynomial, and HB5 fifth degree polynomial. MS3 method of multiple scale third degree polynomial, and MS5 is a fifth degree, and NS is numerical solution. So here we have here compares to amplitude of periodic solutions obtained by analytical methods here, with numerical solutions obtained by the continuation method for the full nonlinear model of the system, when the parametric friction frequency Omega changes as a bifurcation parameter near resonance frequency. So based on the observation of numerical solutions obtained by the continuation method, that in the case of two coexisting solutions, the one with the larger amplitude is stable while the second solution is unstable. So solid lines shows the stable solution and dotted line shows the unstable solution. The presented solutions were obtained from the parameters identified based on the experimental data and given in section in previous we have find these values of drive friction term we find by experimentally. And so the here we have showed this result comparison graphs in the absence of drive friction. Sigma is equal to 0. Here presented branches of previous solution and periodic orbits obtaining using the numerical continuation method. And here if we and in the next slide we have represented. So it can be observed that the branches of the periodic orbits are connected to the fixed point line for y is equal to 0. For y is equal to 0 at points that are period doubling bifurcation. At these points, the stability of the fixed solution changes and it is unstable between these points. Furthermore, the figure shows the branches of periodic orbits obtaining using different analytical methods. The harmonic balance method for stiffness characteristic described by the third HB3 and fifth order polynomial HB5, and the multiple scale method for stiffness characteristic by third or fifth order polynomial. And this time it is isolated from the trivial solution, which is stable over the entire range changes in the frequency omega. So there are also presented amplitudes of periodic orbits obtaining analytically. And in the next figure, here drive friction coefficient omega sigma is equal to 0.009625. So this figure exhibits results for the drive friction value identified on the rail stand. As in the previous figure, the periodic solution branch is isolated from the fixed point, which is confirmed by both the numerical and all analytical solutions. Additionally, experimentally obtained results ES are presented, but only for the stable part of the periodic orbit branch. So for the better insight into behavior of individual analytical solutions of these previous figures, figure 3, 4, and 5, we have represented in the next figure, again, repetition of plots from these figures. In this figure, we have represented multiple scale method results. So we can observe that for a small amplitude, the analytical results by multiple scale and numerical solutions are very close. But for the large amplitude, they have different behavior. The multiple scale MS3 curve shows a less hardening effect than the numerical solution in the amplitude frequency. So if you see here, actually we have three different values of sigma, and we can observe, we can discuss. And the MS5 stable curve represents probably the same hardening effect as numerical solution, but the unstable part of multiple scale MS5 shows a more hardening effect So for the large value of amplitude, the stable and unstable part of MS3 and MS5 are not connected at one point, but numerical response curve meet at one point. So in the next figure, the behavior of the system is shown by using harmonic balance method, which is, so we can see that the analytical results by HBM, both HB3 and HB5, and the numerical solution have a good agreement for small amplitude, but behave differently for the large amplitude. So for large values of amplitude, third degree nonlinearity HB3 solution curves both stable and unstable shows a less hardening effect and as numerical solution. And on the other hand, HB5 curve, both stable and unstable, disappear. So if we see here, it will disappear for the large amplitude. But we notice that the MS3 and HB3 show a common behavior for the large amplitude, which is that both represent a less hardening effect as compared to numerical solution. The stable and unstable solution of harmonic balance method meet at one point for the larger amplitude, but not in multiple scale method. So here we have some references, and thank you.